This is some guidance on how to approach the first problem in Chapter 5 applications. So what we're doing is we're looking at a bunch of data and we're going to try and make sense of it. So for set A, we're asked to find the standard deviation for the distribution of means, symbolized as sigma with that lowercase subtext m right next to it. So I'm going to begin by writing down the formulas for you so you remember them. We take this all step by step. So we know that when we have let me get my pen working here for us, that when we have information about the standard deviation for the population, we have to make some adjustments in order to get to the standard deviation for the distribution of means. And the first thing we have to do is find the variance. And we know that variance is equal to standard deviation squared. We know that to get to the variance for the distribution of means, we take the variance and divide by n, or the number in the sample. And to get to the standard deviation for the distribution of means, we just take the variance for the distribution of means and find the square root. So having those formulas in place, we're all set. Let's write down the key information. In our first problem, we could see that mu, or the population mean, is 65. I'm going to just record these into cells so I can work with the data. We can see the standard deviation is 13, n is 1, m is 67. Before I do any calculations, I'm going to record the rest of the data. And if I look at these problems, I can see that mu for all of them is 65. So I'm going to copy down mu, our population mean. I can look down here and see sigma is the same for each of them. So I will hit Control C to copy it and Control V to paste. N changes. It's 1 in the first example, then 2, then 5, then 25, then 50. And M, or the sample mean, stays the same. As it turns out, we don't even need to know that. So next we'll figure out the variance. And we know that the variance, because it says right here, is just the standard deviation squared. So let me type our equal sign, and I'll click in the cell with the standard deviation and square it. Next, the variance for the distribution of means, we can see right here is the variance divided by n. So equals, we'll click on the variance and divide by n. And finally, the standard deviation for the distribution of means is the square root of the variance for the distribution of means. So we'll take and type in SQRT for square root, and then in parentheses, click in the cell with the variance of the distribution of means. And there we go. Now, to save myself time, I'm actually going to copy this and paste it down. And now we can see that we have all of these answers provided for the standard deviation for the distribution of means. So now we're asked to answer a question. I'll highlight it. What do I notice happens to the standard deviation for the distribution of means right here as n increases right here? And so I'm going to look in these two columns and compare them. And this is for you to look and compare. And so I'm actually going to record the answer for us. So what I see is that as n gets bigger, it looks like the standard deviation for the distribution means gets smaller. So I'm going to write that down. As the number, I'll be nice and clear in my writing, in the sample increases, the standard deviation for, whoops, a typo, I don't want that, for the distribution of means decreases. This occurs because now how could we find the right words? What I need is a little more space here, and I can do this in two ways. I need more space to write. I can either make this box wider this way, or I can just add a couple rows here by highlighting these two rows and clicking insert. Now I have a little more room to write. I think I'm going to do it that way so I can just keep seeing what I'm writing a little better. All right, as the number in the sample increases, the standard deviation decreases. This is because it is far less likely to get extreme scores, far from the mean, if we take the average of larger sample sizes. Thus, the spread of the distribution must be smaller as sample size gets larger. I hope that's adequate. It relates to that dice problem. When we shake more dice, we're less likely to get, say, all sixes or something like that. Like if we shake 25 dice, we're far less likely to get all sixes than if we shake just one or two dice. So hopefully that's a good enough response there. I'll give it a little more room. So next we're asked to find the standard deviation for the distribution of means, but it looks like we're given different information. So here I see we have mu 115, but then it looks like we have variance. The standard deviation squared means variance, so that's 25. N, it looks like we have 44. M, it looks like we have 116. I noticed we didn't even use our M in the last problem. So now I'm going to get the data out of each of these before I begin. I see mu is 16 here. Variance is 4. It says variance now instead of sigma squared, but they're the same thing. N is 30 and M is 14. Here I see mu is 25. Variance, it's still variance, is 50. Let's see. Next we have N is 10 and M is 30. The next problem looks like it's all the same except N is 20, so I'm going to copy and paste. And finally, we have mu is 400. Ooh, here we have standard variance for the distribution of means at 1.8. N is 50. And M is 48. I don't even know if we need to have M in here for this problem. I know we don't because I know the formulas. So let's go on and get the correct solutions. I know that to get the variance for the distribution of means, I just need to take the variance and divide by N. So I'm going to fix this up. And actually, I'm not going to. I'm just going to take equals and I'll click on variance, divide by N. And next, I can copy this formula for all of these. And let's check if it got it right here. Let's see if it clicked on the right cells. I've highlighted the cell and now I'm placing my cursor in the function bar and I see that it did do the right thing. So these should all be good. Now to get the standard deviation for the distribution of means, I just type equals and I get the square root SQRT. That needs to be an equal sign. SQRT parenthesis to show what we're asking for the square root of, and we're asking for this. And now I can simply copy this and paste it down. And so now I can see that we have standard deviation for each of these. And we're asked, what did we notice about the variance for the distribution of means in C and D? Here we go. And what I learned is that I made a mistake. Instead of changing n to 20, I changed n. And I knew that right away because I knew that they could not be the same if n was different. And I remembered that n was different. So it looks like m is still 30 and I made a mistake and I'm glad I caught it. So what I notice about the variance for the distribution of means is that this one is exactly half of this one. So the variance for the distribution of means in D is exactly half of the variance for the distribution of means in C. So I guess I'll observe that and write it down. The variance for the distribution of means in D, I'll do it like this, parentheses around the D so it doesn't look weird, is exactly half of the variance for the distribution of means in C. Why does this occur? Well, I think it occurs because n is twice as great in D. It's kind of weird though, isn't it, right? I need a little more room I can see, so I'm going to add some space by inserting a row. And I'll extend maybe this way. I like that a little better. This doubling is in the opposite direction of n. Now I'll explain that. N is twice. N in C is half as big as n in D. Interestingly, the standard deviation for the distribution of means, remember you can abbreviate this SEM, which is much easier to type, is not following this same the same doubling pattern. This is because the square root needed to obtain SEM. Here we go, I'm adding another row. Insert, click on it, and we get a row. To obtain SEM follows a different curve. Exponential change instead of linear change. All right, so that one's done, best I can do. And we have one last problem to do. Let's transfer the information. U is 65, standard deviation 13, N is 5, M is 67. Here we have 65, 13, and 67 again. So I'm going to see if I can copy this properly this time because I can see that N is 50. We have 25, 50, 20. And what I did was just careless, and I demonstrated this on purpose. So in these problems, you have to pay attention to what you're given. And notice here, I am given variance. I'm not given standard deviation. So let's take this 50 out of here and put it right here under variance where it belongs. That way I won't mess up my formulas. N is 10. And M is 30. Here we have mu is 25, checking carefully, variance is 50 again. N is 20. This is just like the one we had before, isn't it? And M is 30. And our last problem, mu is 115. Variance is 25. I wonder if I recorded that problem correctly. N is 44. And M is 120. So now we're ready to look at our problems. So first off, for these, I still need the variance. So what I have to do is square the standard deviation. So equals standard deviation squared. Enter. I'll copy that using Control-C, use Control-V to paste. Variance for the distribution of means, we get by dividing by n. So we'll go equals, we'll take this and we'll divide each cell by the number in n. And we can just copy and paste this formula down. The cells will reference properly. The standard deviation for the distribution of means is just the square root of the variance for the distribution of means. So we'll enter. I'll copy this down. Now we're asked to get z. And as you know, the formula for z is the same as we've worked with in the past, except now we're using sample mean. So z, in this case, with samples larger than 1, is the sample mean minus the population mean divided by the standard deviation for the distribution of means, which I'll write as SEM, but I could also write as standard deviation for the distribution of means. So let's go ahead and get that formula. Equals M. I'm going to go back and get my parenthesis right away. M minus mu divided by standard deviation for the distribution of means. A z-score very small, 0.34. And I'm going to copy this and paste it down. Interesting. Now we're asked a question. Of all the z-scores above, which would allow you to reject the null hypothesis if alpha was 0.05 in a two-tailed test? How do you know? Well, let's pull up our critical value calculator and see. 0.05 is already here. So our two-tailed test is plus or minus 1.96. So let's just draw a little illustration of that. So if we draw our little graph that we always use, I'm going to draw it in very short form here. Here we go. And we know that we have 1.96 here. Minus 1.96, we have 1.96 here. And so any scores that are in these tails, we reject. This is our rejection region, and in the center here is our fail region. So let's plot these out. The 0.34, I don't even have to think about. The 1.087 is going to be right about here. So this is B. 2.236 is going to be about here. So this is C. 3.162 is going to be out here. So that's D. 6.663 is going to be out here. And so that's E. So I see that the only one that falls in the fail region is B and A, which I didn't draw, which is right about here. So those two are fail. The other ones are reject. I think I'm just going to add a column and write that. Fail, fail, and then reject, make our statistician happy. And we'll reject these others. And so now we can write for our answer. Problems B, B, C, D. I'm going to fix that mistake in a minute. allow us, this is not B, problems C, D, and E allow us to reject the null hypothesis. I know because these scores are more extreme than the cutoff point of plus minus 1.96. And that's enough. That's adequate. And that problem is solved.